Good morning, everyone. Now, our next chapter is chemical kinetics. Introduction. Chemical kinetics is the branch of chemistry which deals with the rates of chemical reaction, the factors which affect the reaction rates, and the mechanism by which these reactions proceed. In other words, chemical kinetics tells us how fast a particular reaction takes place, at what temperature at what mechanism it follows. It also tells us how the reaction rate is dependent on variables like temperature, pressure, and the concentration of the reacting species, etc. The chemical reactions can be classified into following categories on the basis of their speeds. First is instantaneous reactions. The reactions which occurs at very fast speed. These reactions occur as soon as reactants are mixed and is practically not possible to measure the speed of such reactions by ordinary methods. Such reactions include several ionic reactions, neutralization reactions of acid and bases, etc. Examples are AgNO3 plus NaCl is equals to AgCl plus NaNO3. Second is extremely slow reactions. Those reactions which proceed at very slow speed, for example, rusting of iron, combination of hydrogen and oxygen at ordinary temperature, etc. These reactions occur at such slow speed that it is not possible to determine the rate of these reactions. Third is reaction which proceed at measurable speed. These are chemical reactions which proceed at moderate speed which can be easily measured. Some example of such type of reactions are hydrolysis of ester. Ethyl acetate plus H2O give rise to acetic acid plus ethyl alcohol. Inversion of cane sugar, decomposition of HI are the examples of these reactions. Different chemical reactions proceed at different rates. An obvious reason for this is that a chemical reaction involves breaking of bond in the reactant and formation of new bonds in the product. The energy required for bond breaking and energy evolved for bond formation is different for different reactions. That is why different reactions proceed at different rates. The instantaneous reaction involves just combination of ions that are already present in solution. Hence, these reactions occur at very fast rate. The reaction with measurable rates are the focus of attention in chemical kinetics. Chemical kinetics is concerned with the following aspects. First, the rate of reaction and the rate laws. Second, what is the effect of temperature, pressure, concentration, and catalyst on the rate of the reaction? Third is what is the mechanism or the sequence of step by which the reaction occurs. Next topic is rate of a chemical reaction. The rate of a chemical reaction or the reaction velocity may be defined as the change in concentration in any one of the reactant or the product per unit time. For example, consider a reaction A is equals to A is converted into B. Thus, rate of reaction is equals to decrease in the concentration of A divided by time taken, or also it is equal to increase in concentration of B divided by time taken. Units of rate of reaction. Rate of reactions has units of concentration divided by time. The concentration is usually expressed in moles per liter. For gaseous reactant, instead of concentration, we take pressure in atmosphere and time may be expressed in seconds, minutes or hours. Therefore, the unit of the reaction rate are as follows: mole per liter per second, deci, mole decimeter cube per second, mole per liter per minute, mole per liter per hour. For gaseous reactants or products, the concentration term is expressed in terms of partial pressures. Therefore, the units of the rate of reaction will be atmosphere per second, atmosphere per minute, or atmosphere per hour. The molar concentration of reactants in products keep on changing with time. Therefore, the rate of reaction is not uniform throughout but keeps on varying. Therefore, it is more appropriate to express the rate of reaction at particular instant of time. Such a reaction rate is called instantaneous rate of reaction and it is defined as the change in the concentration in any one of the reactants or products at particular instant of time. Next is expressing the instantaneous rate of reaction. According to law of mass action, the rate of reaction depends upon the molar concentration of the reactant. As the concentration of reactant changes with time, so that the rate of reaction also changes with time. Therefore, it is more appropriate to express the rate of reaction at particular instant of time. To express the rate of reaction at a small interval of time, dt is taken and it is assumed that the rate of reaction remains constant in this interval of time. If dx is the small change in the concentration of any one of the reactant or the product, then the rate of reaction is expressed at rate of reaction is equals to dx by dt. In case of reactants, concentration decreases with time, therefore a negative sign is put before dx by dt, that is minus of dx by dt. On the other hand, the concentration of products increases with the time and hence a positive sign is written before dx by dt, that is plus dx by dt. Consider the following reaction: A plus B give rise to L plus M. The rate of reaction is expressed in terms of fall of concentration of a reactant or increase in the concentration of the product. Thus, the rate of reaction based on the rate of change of concentration of each species is written as rate of reaction is equals to dx by dt is equals to minus of d of concentration of A divided by dt is also equals to minus of d concentration of B divided by dt is equals to plus dl by dt is equals to d concentration of m by dt. It may be emphasized that the rate of reaction is always positive. The negative sign in the above expression indicates that the fall in the concentration of the reactant, whereas the positive sign in this expression indicates the increase in the concentration of the product with the passage of the time. Here D into concentration of A and D into concentration of B represent the small decrease in the concentration of reactants A and B, and DL and DM represents the small increase in the concentration of the products L and M. For general reaction, small a plus capital A plus B in small b plus small b into capital B is equals to LL plus MM. The rate of reaction is written as follows: dx by dt is equals to minus 1 by a of d into dA by dt is also equals to minus of 1 by b into concentration of dB divided by dt. Similarly, to solve 1 plus 1 by m concentration of m divided by dt. Now next is measuring the rate of the reaction. The rate of reaction can be measured by plotting a graph between the concentration of any one of the reactants as a function of time. The concentration of any one of the reactant or the product is measured at different intervals of time. For this, it is necessary that all other variables except concentration, which may affect the reaction rate, remains constant. Usually, a reaction is carried out and a small amount of reaction mixture is withdrawn at small intervals of time. The reaction mixture is cooled at a temperature below 0 degrees Celsius by keeping it in freezing mixture. By doing so, that the reaction is arrested. That is, no further reaction takes place. Now, the concentration of any one of the reactant or products is determined by suitable methods, usually titration, etc. After determining the concentration of reactant or product, a concentration time curve is plotted. It is not always required to stop the reaction for measuring the concentration of any species at variable time intervals. The same information can be obtained by noting the changes in observable properties like change in color, change in pH, volume, pressure, optical rotation with time. Accordingly, the graphs are plotted to calculate the rates of reaction. All these methods will be taken up as we proceed in the chapter. However, if the change in concentration of a reactant or a product is measured with time, then the rate of reaction is determined as follows. In such type of concentration time curves, the reaction rate is determined by two methods. First is the rate of reaction at any instant of time can be determined by drawing a tangent to the concentration time curve at that particular instant. The slope of the tangent then gives the required rate of the reaction at that instant. The slope of the curve tan theta is equals to OA divided by OB is equals to del x by del t is also equals to dx by dt. Second is a small change in concentration dx in a small time interval dt is noted directly from the concentration time curve. Assuming that the rate of reaction remains constant during the small interval of time, the quantity dx by dt gives the required rate. Now, the factors affecting the rate of the reaction. The rate of reaction is influenced by the following factors. First, nature of reactant. Second, concentration of reactant. Third, temperature of the system. Fourth, presence of a catalyst. Fifth, exposure to radiation. Sixth, and last is nature of the solvent. For reaction in heterogeneous system in which a reactant is in solid state, the surface area of reactant also becomes an important factor which affects the rate of reaction. By studying these factors which affect the reaction rates, it becomes possible to control the rate of reaction. First is nature of reactant. Substances differ in activity and hence in the rate at which they react with other substances. For example, active metal displaces hydrogen rapidly and vigorously from acid, while the excess active metal reacts slowly. Hence, the rate of reactions are affected by the nature of the reactant. Following examples clearly show this effect. Oxidation of nitric oxide and carbon monoxide in air. Oxidation of nitric acid is fast and carbon monoxide in air is slow. Above two reactions seen identically. There are some number of moles of reactants and products in both the cases, and both are oxidation reactions, but they differ in their rates. The reason is that the nature of reactant, that is NO and CO, must be different, hence there is difference in rate of these reactions. Under similar conditions, the first reaction is fast while the second is slow. So rates of reaction are influenced by the nature of the reactants. A chemical reaction involves the breaking of old bonds and formation of new bonds. The reactivity of a substance is therefore is related to the ease with which the specific bonds are broken and the number of such bonds evolved. As the amount of energy required to break the bonds is different in different reactants, hence the rates of reaction also vary with the nature of the reactant. Second is concentration of the reactant. It has been observed that the rate of chemical reaction keeps on decreases with time. The concentration of reactant is maximum at the start of the reaction, and therefore the rate of change of concentration is also maximum. As the concentration of reactant decreases, it brings about the corresponding decrease in the rate of reaction. This clearly indicates that the rate of reaction is directly proportional to the concentration of the reactants. The change of concentration of the reactants and therefore the rate of reaction with time is shown in figure 2. From above figure, it is clear that at the start of the reaction, the rate of reaction is large and it decreases with the passage of time. Therefore, to increase the rate of reaction, we should increase the concentration of one or all the reactants. In a gas phase, the reaction in pressure of the reactant gases increases the rate of reaction. With increase in pressure, the number of molecules per unit volume increases and therefore rate of reaction increases. The effect of concentration of reactants on the reaction rate may be explained in terms of collision theory. According to collision theory, the rate for reaction depends upon the number of collisions per second between the reactant molecules. By increasing the concentration of one or all the reactants, the number of collisions increase and it leads to an increase in the rate of the system. Third is temperature of the system. In generally, an increase in temperature increases the rate of almost all chemical reactions. Besides increasing the rate of reaction, in many cases it is observed that the temperature even initiates the reaction. For example, hydrogen and oxygen do not react at room temperature but react radially to form water when electric spark is passed through them. The rate of all reaction increases with increase in temperature. A general approximate rule is that the rate of most of the chemical reactions becomes double or even triple for every 10-degree rise in their temperature. This is also called temperature coefficient, which is defined as the ratio of rate constant of reactions at two different temperatures differing by 10 degrees Celsius. Next is explanation of the effect of temperature on rate of reaction. The increase in reaction rate with increase in temperature is explained on the basis of collision theory. According to collision theory, the chemical reaction occurs as a result of collision between the reacting molecules. However, all collisions do not result in chemical reaction. Only effective collisions between the reactant molecule results in the formation of chemical reactions or products. According to collision theory, only a small fraction of collisions is effective in bringing about the chemical change and rest of the collisions are ineffective. For an ineffective collision, the colliding molecules must have more than or equal to certain minimum amount of energy called threshold energy. Thus, the threshold energy may be defined as the maximum energy which must be possessed by the colliding molecules to cause a chemical reaction on collision between them. If the energy of the reacting molecules is less than this value, collisions will be ineffective. All the molecules in a substance do not possess the same energy. Thus, there is a distribution of energies among the reacting molecules. If the energy of molecules are plotted against the corresponding fraction of molecules, at a particular temperature, a curve of the type shown in figure 3 is obtained. This is called Maxwell distributions of energies. E corresponds to the minimum or the threshold energy required for causing effective collisions. The molecules having energy equal to or greater than E will result in the formation of products. To explain the effect of increase in temperature on the number of effective collisions, consider the energy distribution of molecules at two different temperatures. Therefore, we may conclude that the rate of reaction becomes almost double for every 10-degree rise of temperature. Next is concept of activation energy means an energy barrier. Familiar reactions such as burning of coal in air, combustion of hydrogen and oxygen gases do not occur unless some extra energy in one form or the other form is supplied to them. This is because in such reaction, the reactant molecules do not possess energy equal to or greater than threshold energy under normal conditions, so there is no reaction. Thus, some extra amount of energy has to supply to the reactants to bring their energy equal to the threshold energy, and then the reaction starts. The excess energy which must be supplied to the reactants so that their energy becomes equal to the threshold energy is called the activation energy EA. It is equal to the difference between the threshold energy for the reaction and the energy possessed by all the reacting molecules. That is, activation energy is equals to threshold energy minus energy possessed by the reacting molecules. It is graphically shown in figure 4 that for a reaction to occur, the colliding molecules have to absorb some energy and cross the activation energy barrier. When the colliding molecules possess energy equal to activation, an intermediate activated complex is formed which is different from the reactant as well as the product. Consider a reaction A2 plus B2 is equals to 2 of AB. The reactant have energy ER. The reaction cannot occur until the colliding molecules A2 and B2 have sufficient energy equal to threshold energy E2 to form an activated complex. In the activated complex, the AA and BB bonds are breaking and AB bonds are forming as shown in the figure. In case of oxidation of NO, the activation energy is small and thus only a small increase in the energy enables reacting species to cross the energy barrier to form NO2. Therefore, the reaction is faster at room temperature. However, in case of oxidation of CO, the activation energy is high, so large amount of energy is required by reactants to cross the activation barrier. Hence, the reaction is slow at room temperature, and thus we conclude that if activation energy is low, the reaction is fast, and if activation energy is high, then reaction will be slow. The mathematical relationship between the reaction rate and the temperature is given by rate of reaction is equals to Z e raised to power EA divided by RT, where Z is the collision frequency of binary collisions and factor e raised to the power minus EA divided by RT represent the fraction of molecules which have energy greater than activation energy EA. For reaction involving simple molecules, the rate of reaction can be predicted by this equation, but for the complicated molecules, the value of reaction and rates are found to be less than those calculated by using above equation. This is because in such reactions, the rate of reaction not only depend on energy factor but also on orientation factor. That is, the colliding molecules must have proper orientation at the time of collision. Hence, an addition factor P called the probability factor or steric factor is inserted in the above expression. So, rate of reaction is equals to P into ZE into e raised to power A divided by RT. The values of P varies from unity to about 10 ki power minus 8 depending upon the nature of the reactant. Fourth factor is presence of catalyst. A catalyst is a substance which increases the rate of chemical reaction and can be covered chemically unchanged at the end of the reaction. For example, manganese dioxide speed ups the thermal decomposition of potassium chlorate. Manganese dioxide acts as a catalyst in the reaction and can be recovered unchanged at the end of the reaction. Following point must be about noted about the function of catalyst. The catalyst does not change delta E or delta H of a reaction. It is clear from the figure 5 that the addition of catalyst does not change in the energies of the reactant and the products EP, so that delta E remains the same. Second, although the catalyst speeds up the reaction, but it does not affect the position of the equilibrium in case of reversible reaction. This is because the activation energy for the forward reaction and the backward reaction is reduced to the same extent. As a result, the increase in rate of the backward and forward reaction is same, and hence the position of equilibrium remains unaffected. Hence catalyst increases both the rate, hence the equilibrium is attained earlier. Fifth is exposure to radiations. In some cases, the rate of reaction is considerably increased by the use of certain radiations. The photons of these radiations possess sufficient energy, E is equals to h nu, to break certain bonds in reactants. For example, reaction of hydrogen and chlorine takes place very slowly in the absence of light. However, in the presence of light, the reaction takes place very rapidly. Next and last is nature of solvent. Nature of solvent also affects the rate of the reaction. These effects can be studied under the following properties of solvent: magnitude of dielectric constant of the solvent, polarity of the solvent, and effect of the solvent. Now we will do concentration dependence of reaction rates. Law of mass action. When a chemical reaction proceeds, the reactants get converted into products. As a result, the concentration of the reactants decreases while that of products increases. The quantitative relationship between the rate of reaction and molar concentration of reacting substance is known as law of mass action. According to this law, at a given temperature, the rate of a chemical reaction is directly proportional to the product of the molar concentration of the reactant. Consider a simple reaction. AA plus BB is equals to product. According to law of mass action, the rate of reaction may be written as R is equals to K into molar concentration of A raised to the power B into molar concentration of B raised to the power B, where A and B are the molar concentration of reactants, K is the constant of proportionality, and it is called rate constant or velocity constant. Now, if the concentration of each of the reactant is unity, then rate of the reaction is equals to the K. Thus, the rate constant of a reaction at given temperature may be defined as the rate of the reaction when the concentration of each reactant is unity. Hence, rate constant is also known as a specific rate reaction rate. Next, rate law expression. The actual dependence of rate on concentration of reactants or products is measured experimentally. Thus, for a reaction AA plus BB is equals to product, the dependence of the rate of the reaction on concentration is found to R is equals to K A raised to the power molar concentration of A raised to the power P into molar concentration of B raised to the power Q, where P and Q are experimentally determined powers of concentration of reactants A and B respectively, on which the rate of the reaction depends. The power P and Q may or may not be equal to the coefficients A and B in the reaction. Thus, expression 2 is called rate law or rate equation. Rate law differs from the law of mass action. The rate law gives experimentally observed dependence of the rate on the concentration of reactants. The power of concentration of reactants in rate law expression may or may not be same as the coefficients of concentration in the balanced chemical equation. In above general equation, according to law of mass action, R is equals to K into molar concentration of A raised to the power small a into molar concentration of B raised to the power B. The rate law expression is R is equals to K into a molar concentration A raised to the power P and B into molar concentration of B raised to the power Q. Order of reaction. Order of reaction is defined as the sum of the powers to which the concentration terms are raised in rate law equation to express the observed rate of the reaction. Thus, the order of reaction is n is equals to p plus q. If n is equals to 1, the reaction is said to be first order. If n is equals to 2, the reaction is said to be second order, and so on. Some Common examples of reactions of different orders are given below. Reactions of first order, that is decomposition of N2O5, decomposition of ammonium nitrate in aqueous solution. Reactions of second order, decomposition of NO2. Reactions of third order are reaction between NO and Cl2, reaction between NO and O2. Reaction of fraction order, decomposition of acetaldehyde, a reaction between H2 or B2 in which the order of the reaction is in the fraction. Some examples or numericals on the based of the above formulas. Now, first we will do zero order reaction. A number of reactions are known in which the rate of the reaction is independent of the concentration of the reactant. For example, the decomposition of ammonia at the surface of metals like platinum. 2NH3 in the presence of platinum gives rise to N2 plus 3 of H2. The rate of reaction is independent on the concentration of ammonia, that is R is equals to K into NH3 raised to the power 0. R is equals to K, then order of the reaction is equals to 0. Thus, our reaction is said to be zero order if its rate is independent on the concentration of the reactant. In such reactions, the rate of reactions remains constant throughout. The amount of the substance reacted is proportional to the time. Zero order reactions are relatively uncommon. Many photochemical reactions and heterogeneous reactions have been found to be of zero order. Photochemical reactions are reactions which takes place in the presence of light are called photochemical reactions. Many photochemical reactions, example formation of HCl from H2 and Cl2 are examples of zero order reaction. The kinetics of the combination reaction of H2 and Cl2 in the presence of light can be studied in the laboratory by a simple experiment. A test tube filled with a mixture of H2 and Cl2 gas is inverted in a trough containing water. The setup is exposed to sunlight and the photochemical reaction takes place. The HCl formed is soluble in water. As a result, the level of water rises in the test tube. It is found that after some time, the amount of H2 and Cl2 decreases, but the concentration remains unchanged. This proves that the photochemical reactions between H2 and Cl2 is of zero order. Next is heterogeneous reactions. Zero order reactions are found in heterogeneous system. A heterogeneous system, the reactants, products, and the catalyst are present in different phases. The well-known examples of heterogeneous reactions with zero order are decomposition of hydrogen iodide on the surface of gold, and second is decomposition of ammonia on the surface of metals like platinum, molybdenum, or tungsten at high temperatures. In such reactions, the reactant is adsorbed on the surface of the catalyst where it is converted into the products. At low concentration, the reaction is first order, but when the surface of the catalyst becomes fully covered with the reactants, the reactions become zero order. On increasing the concentration of the reactants, the reaction rate does not change. In other words, the rate becomes independent of the concentration and therefore becomes zero order reaction. For example, the decomposition of NH3 on the surface of linearly divided platinum is first order when the pressure of NH3 in the system is low. However, at higher pressure, when the surface of catalyst becomes fully covered with the layer of NH3 molecules, the reactions become zero order. Some enzymes catalyst reactions are also of zero order reaction. Now next is integrated rate expression. We have learned that the instantaneous rate of reaction is given by differential rate law equation. For example, for a general reaction AA plus BB is equals to product, the differential rate law equation dx by dt is equals to K into molar concentration of A raised to the power A molar concentration of B raised to the power B. The differential form of the rate law is transformed to integrated form of the rate equation. Now first we will do zero order reaction. In a zero order reaction, the rate is independent of the concentration of the reactant. Consider a general zero order reaction. A is equals to A is converted into products. Let A be the concentration of the reactants and K is the rate constant for zero order reaction. Since the rate of reaction is independent of the concentration of A and thus R is equals to minus of dA into dt is equals to K into A raised to the power 0. This is differential rate equation. From rearranging above equation we get minus d of A is equals to K dt. Now we will integrate this equation and we will get minus of A is equals to KT plus I, where I is the constant of integration and the values of I can be calculated from the initial concentration. Let the initial concentration of A be at temperature T is equals to 0. Then the value of I is equals to minus of A naught. Now we will substitute the value of I in equation 1 and we will get K is equals to 1 by T into initial concentration A naught minus final concentration A. This is integrated rate expression for zero order reaction. The rate constant K can be calculated if we know the concentration of A at any time T and the initial concentration A naught. Alternatively, the rate constant, the other formula rate constant of first order reaction is equals to X is equals to K by T. It shows that for a zero order reaction, the amount of substance reacted is proportional to the time. Now here are some important characteristics of zero order reaction. The integrated law equations for zero order reaction are Kt is equals to A naught minus second is A is equals to minus Kt plus A naught. Third is equals to K is equals to 1 by T A naught minus At. Now we will make the graph against this. Now we will do half-life of a zero order. Half-life T half of a reaction is the time required for the concentration of reactant to decrease to its half initial value, that is T is equals to T half and the concentration of A is equals to A naught by 2. Substituting the value in the integrated rate equation and we will get T half is equals to A naught by 2K. Thus the half-life of a zero order reaction is directly proportional to the initial concentration of the reactant. This means if the initial concentration of reactant is made double, the time required for the to be reaction to be half completed is also double and so on. Units of rate constant for the zero order is mole per liter per time. Kinetics of first order reaction. A reaction is said to be first order if the rate depends upon one concentration variable only. Consider first order reaction A is converted into P product. If the initial concentration of A is small a moles per liter and let x moles of the reactant get unchanged into products in time T, then the concentration of A after T is A minus x moles per liter. Then the rate of reaction is directly proportional to A. dx by dt is directly proportional to A minus x and we will move the proportionalities, remove the proportionalities and the reaction become dx by dt is equals to k into A by x. Now we will arrange the equation 1. Now we will get dx divided by A minus x is equals to kt. Now we will integrate this equation and we will get the formula of k for the first order reaction, that is k is equals to 2.303 t by log of A by A minus x. If the initial concentration of A is C naught at temperature T is equals to 0, at time T is equals to 0, and at time T the concentration of A is Ct, then putting A is equals to C naught and A minus x is equals to C2 in equation 4, we will get K is equals to 2.303 T by log C naught by Ct. Similarly, we can calculate the different formulas for this reaction. Now, the important characteristics of first order kinetics are: first order reaction must obey any one of the following rate equations. K is equals to 2.303 by T log A by A minus x. Second is K is equals to 2.303 T by log C naught by Ct. Third is Ct is equals to C naught into K into minus e raised Ct is equals to C naught into e raised to the power minus Kt. In a reaction of first order, the rate equation Ct is equals to C naught into e raised to the power minus Kt means that the reaction never proceeds to the completion because Ct can become 0 only at infinite time t. First order reaction can be tested by following method: by substitution methods and by the graphical methods we can calculate the first order reaction. Now we will do calculation of a rate constant when initial concentration is not known. By this formula we can calculate the is. Now we will do half-life period of a first order reaction. T half of a reaction is the time required for the concentration of the reactant to reduce half of its original value. The integrated rate equation T is equals to 2.303 divided by K log into A by A minus x. If T is equals to T half of the reactant has reacted, X is equals to A by 2. Writing half lifetime as T 1 by 2 and substituting the values of X in equation 12, now we will get T half is equals to 0.693 by K. The initial concentration term A does not appear in the equation. Thus, half-life of a first order reaction is independent of initial concentration of the reactant. Similarly, it can be shown that in a first order reaction, the fractional like periods, that is T 1 by 3, T 3 by 2, etc., is also independent of initial concentration of the reactant. Now, fractional life method can also be used to detect whether a given reaction is of first order or not. Units of rate constant. Units of rate constant of this are per second, per minute, per hour, respectively. Now there are some examples of the first order reaction. The first order reactions are broadly divided into two types. First order gas phase reaction first, and second is first order reaction taking place in solution. Gas phase reactions of first order are comparatively few. In this reaction, the progress of reaction may be followed by measuring the volume or pressure, the gaseous reactants or products. Whereas the first order reaction taking place in solution, the concentration of reactant is measured at different intervals of time. Kinetics of some common first order reaction is taken up in the following discussion. For the sake of simplicity, the examples of first order reactions have been divided into three categories. Decomposition reactions of first order reaction involving isomeric change, and pseudo unimolecular reactions of first order. Now first we will do decomposition reactions of first order. Now decomposition reaction of first order as decomposition of nitrogen pentoxide. Nitrogen pentoxide is a volatile solid which decomposes in gaseous form or in its solution in inert solvents like carbon tetrachloride, chloroform, etc. The reaction is presented as N2O5 is decomposed into N2O4 plus half of O2, and N2O4 is similarly decomposed into 2 of NO2 solution. The kinetics of this reaction may be studied in two ways. By measuring the concentration of N2O5 in solution at different intervals of time. Second is by measuring the volume of oxygen gas produced at different intervals of time. In first case, the following rate equation is used. K is equals to 2.303 T log A by A minus X. However, in second case, as both N2O4 and NO2 remain soluble in solution, while oxygen gas escapes, thus the volume of oxygen gas collected is measured at different intervals of time. The total volume of oxygen collected at the end of the reaction gives a measure of the total concentration of N2O5 taken initially. That is A. If Vt is the volume collected at any time and V infinite is the total volume collected at end of the reaction, then it is obvious that V infinity is directly proportional to the initial concentration of N2O5, that is A. Vt is directly proportional to the amount of N2O5 decomposed, that is X. Now we will get V infinity is equals to A and Vt is equals to X. Substituting for A and X in above equation, we will get K is equals to 2.303 T into log V infinity divided by V infinity minus Vt. So both forms of rate equation are used depending upon the quantity used. Now here is an example of these reactions also. Second is decomposition of ammonium nitrate. Ammonium nitrate in aqueous solution decompose at room temperature according the following reaction. NH4NO2 aqueous is decomposed into 2 mole of water plus N2. The progress of reaction is studied by measuring the volume of nitrogen produced at different intervals of time. The rate equation used is K is equals to 2.303 T into log into V naught minus V infinity. Here is the solved example of this. Third is decomposition of benzene diammonium chloride. Benzene diammonium chloride in its aqueous solution decomposed according to the following reaction. Benzene diammonium chloride in aqueous solution is decomposed into chlorobenzene plus N2. The progress of the reaction can be studied by measuring the volume of nitrogen gas collected at different intervals of time. The rate equation for this reaction is K is equals to 2.303 divided by T into log V infinity divided by V infinity minus Vt, where V infinity is the volume of N2 collected at the end of the reaction and Vt is the volume of N2 at any time t. Here is the example of this reaction also. Now next is decomposition of hydrogen peroxide. The decomposition of hydrogen peroxide taking place according to the reaction. H2O2 is decomposed into H2O plus half mole of water. The reaction is catalyzed by the presence of finely divided platinum. The progress of the reaction is studied by two methods. First, by measuring the volume of the oxygen evolved at different intervals. The rate constant can be calculated by the using equation K is equals to 2.303 divided by T into log V infinity divided by V infinity minus Vt. Second, by estimating the concentration of H2O2 left at the different intervals by titrating H2O2 solution against K-manophore solution. This can be done by withdrawing small amounts of H2O2 solution, say 5 ml, at regular intervals and titrating it against standard K-manophore solution. The volume of KMnO4 used will be directly proportional to the concentration of H2O2 left behind at an instant. The volume of KMnO4 used before the starting of the reaction, that is at T is equals to 0, gives the initial concentration of the H2. Thus, it is obvious that before the start of the reaction at T is equals to 0. So the first order reaction rate is equals to K is equals to 2.303 T log into A minus X. Here A is directly proportional to V naught and A minus X is directly proportional to Vt. So we will get the first order reaction for this is K is equals to 2.303 T divided by log V naught minus Vt. The decomposition of H2O2 obeys this rate equation and it is found to be of first order reaction. Now next is thermal decomposition of azoisopropane. Now we will do this thermal decomposition of azoisopropane. Will do this in the similar manner. Now the formula is K is equals to 2.303 T divided by log Pi into 2Pi minus Pt, where Pi is the initial pressure at T is equals to 0 and Pt is the pressure of reaction mixture at any time T. Now here are some examples of this. Next is first order reaction involving isomeric change. Isomeric conversion of N-chloroacetate into para-chloroacetate is an example of first order reaction. The isomerization takes place in the acidic medium, which is as follows. The isomerization reactions occur when N-chloroacetyl anilide is treated with Ki solution in acidic medium. The study of kinetics of this reaction is based upon the fact that only N-chloroacetate anilide reacts with Ki in acidic medium to liberate iodine, whereas para-chloroacetal aldehyde does not liberate iodine. N-chloroacetate reacts as follows. A known volume of reaction mixture is withdrawn at different intervals and the iodine liberated is measured by titration against the standard solution of KMnO solution of sodium thiosulfate using starch as indicator. The volume of hypo solution used at T is equals to 0 is proportional to the amount of I2 liberated, which in turn is proportional to the initial concentration A of N-chloroacetyl anilide. That is, A is inversely proportional to N naught. The volume of hypo solution used at time T is proportional to the amount of I2 liberated, which in turn depend upon the concentration of N-acetanilide at the time T, that is A minus X. Thus, A minus X is directly proportional to Vt. Substituting the equation in the first order reaction, now we will get K is equals to 2.303 by T into log V naught by Vt. Here is a numerical based on this topic. Now next is pseudo order reaction. These are reactions which are not unimolecular yet. They obey first order equations. Some examples of such reactions are hydrolysis of ethyl acetate and inversion of cane sugar. In these reactions, there are more than one reactant, but the rate of reaction depends on the concentration of any one of the reactant. Consider a general reaction A plus B give rise to products. Rate is equals to K into concentration of A into concentration of B. The molecularity of reaction is 2, so it's a bimolecular reaction. However, when one of the reactant is present in large excess, then its concentration remains practically constant during the reaction. Suppose the reactant B is present in excess and its concentration remains practically unchanged. Under such conditions, we may write R is equals to K naught into concentration of A, where K naught is equals to K into B. Thus, the reactions appears to be of second order but follows first order kinetics. Thus, the reactions which appear to be of higher order but actually follows first order kinetics are called pseudo first order reactions. Consider the hydrolysis of ethyl acetate. If we will do the hydrolysis of ethyl acetate, it will give acetic acid and ethyl alcohol. The molecularity of this reaction is 2, so it's a bimolecular reaction. The concentration of ethyl acetate changes during reaction while water is present in high concentration, that is a solvent. and thus its concentration remains practically constant. Therefore, the rate of reaction depends only on the concentration of ethyl acetate, and hence it is a first order reaction. Thus, the reaction appears to be of second order but follows first order kinetics. Thus, the reactions which appears to be of higher order but actually follow first order kinetics are called pseudo first order reactions. An important example of this is inversion of cane sugar to give glucose and fructose. In this case also molecularity is true while the reaction follows first order kinetics. Now we will do kinetics of hydrolysis of ethyl acetate. Concentration of acetic acid formed can be measured by titrating the reaction mixture against standard solution of NaOH. This reaction is acid catalyzed, but the concentration of mineral acid used as catalyst remains the same throughout. However, it will consume some definite volume of titrating substance, that is NaOH, at the start of the reaction, that is at T is equals to 0. Acetic acid is not formed. Volume of NaOH used at the start is equals to V0. Volume of NaOH used at the time T is equals to Vt. Because the amount of acetic acid formed at any time T depends upon the amount of ethyl acetate that has been reacted, that is X. So X is equals to Vt minus V0. Now we will substitute this in the first order reaction. Now we will get the order K is equals to 2.303 T log V0 V infinity minus V0 divided by V infinity minus Vt. This is the expression of first order rate reaction of hydrolysis of ethyl acetate, and here is a numerical which is based on the hydrolysis of ethyl acetate. Next is inversion of cane sugar. Inversion of cane sugar, that is sucrose, in the presence of mineral acid is an example of pseudo unimolecular reactions. It takes place according to the equation. Sucrose solution is a dextrorotatory with specific rotation of plus 66.5 degree. In this reaction, the hydrolysis of dextrorotatory sucrose produces equimolar mixture of glucose, which is dextrorotatory, and fructose, which is levorotatory. The lever rotation of fructose is minus 92 degree, which is more than the dextrorotation of glucose being 52.5. As a result, the mixture of fructose and glucose is a levorotatory. So on hydrolysis, the dextrorotatory cane sugar solution changes into levorotatory mixture. Hence, the reaction is called the inversion of cane sugar. As the reaction proceeds, the plane of polarization of light changes. Therefore, the reaction kinetics is studied by nothing angles of rotation of reaction mixture at different intervals using a polarimeter. In the beginning, at t is equals to 0, the rotation of light will be to the right. Hence, the reading on the polarimeter will be positive. As the reaction proceeds, the rotation of light keeps on decreasing and finally becomes negative. Thus, the reading on the polarimeter also decreases, becomes 0 and ultimately becomes negative. The rate constant for the change in optical rotation can be calculated as follows. Say angle of rotation at the start of the experiment is equals to R0, angle of rotation at any time RT, and angle of rotation as infinite time is equals to R infinity. So we can say that X is directly proportional to R0 minus RT, and A is directly proportional to R0 minus R infinity. Now we will put this equation in the first order reaction, and we will get K is equals to 2.303 divided by T into log R0 minus R infinity into RT minus R infinity. The constancy in the value of K at different intervals shows that it is a first order reaction. It is observed that the value of rate constant depends upon the concentration of S positive ions that comes from mineral acid that act as a catalyst. Here is the example which is based on the inversion of the cane sugar. Now next is kinetics of second order reaction. A reaction is said to be second order if the rate depends upon the concentration terms which may or may not be the same. Therefore, there are two types of second order kinetics. First, reaction involving one type of reactant. In this type of reaction, both the concentration terms refers to the same reactant. Considered 2 moles of A are converted into products. So the rate of reaction is equals to R is equals to K into concentration of A square. Second, reaction involving two different reactants. In such reaction, the concentration term refers to the two different reactants. Consider a general reaction A plus B is equal give rise to product. So K is equals to R is equals to K into A into B. The constant term K as the rate constant for second order reaction. The integrated rate equation for these two types of second order derived are as follows. First, rate equation for reactions involving only one type of the reactions. Considered a general second order reaction 2A give rise to products. So the rate of the reaction is equals to R is directly proportional to A square. Now we will calculate this by the formula dx square and integrate this formula at the whole, and at the last we will get K is equals to 1 by T into x into A minus x. In the initial concentration, if the initial concentration of A is C naught at T is equals to 0, and at time t the concentration of A is Ct, that is A is equals to C naught and A minus x is equals to Ct. Subtracting equation 4 from 5th, we will get x is equals to C naught by Ct. Putting the value of A and A minus x and x from equation 4th, 5th and 6th into equation 3rd, we will get K is equals to 1 by T 1 by T into 1 by Ct minus 1 by C naught. This is an useful form of second order reaction as we can directly calculate the concentration of reactant species at any time, that is T, the initial concentration C naught and the rate constant K are known. Important characteristics of second order kinetics. Our second order reaction must obey any of the following rate equations. K is equals to 1 by T x into x divided by A into A minus x. Second is K is equals to 1 by T into 1 by Ct minus 1 by C naught. Third is equals to K is equals to 2.303 T into A minus B log B into A minus x and A into B minus x. Second order reactions can be tested by the following methods. First, substitution methods. In this method, the values of A, B and the amount of reacting substance X at different time intervals are substituted in the rate equations and the values of rate constant is calculated. The constants in the value of K indicates the reactions of second order. Second is graphical method. Since second order rate equation K is equals to 1 by T into 1 by Ct minus 1 by of C naught may be rewritten as Kt is equals to 1 by Ct minus 1 by C naught. This is an equation of straight line y is equals to mxc when a graph is plotted between 1 by Ct and time t at various intervals of time. A straight line is obtained showing that the reaction is of first order. The slope of the line is equals to the K, which directly gives the value of the rate constant. Next is half-life period of second order reaction. For a simple second order kinetics 2 is equals to product and the half-life time for this reaction is equals to 1 by K into 1 by A. Thus the half-life period for the second order reaction is inversely proportional to the initial concentration of the reactions. Similarly, it can show that the time required for completion of any fraction of the second order reaction is inversely proportional to the initial concentration. Let us calculate the time taken for 2/3 of the reaction to be completed, that T is equals to 2 by 3 when X is equals to 2 by 3A, and when we will substitute this reaction and we will get T 2 by 3 is equals to 1 by K into 1 by 2A. The fractional life method can also be used to test whether a given reaction is of second order or not. The units of second order rate constants are mole per liter per time or liter mole per time. Thus, if the time is expressed in seconds, minutes or hours, the units of K will be liter per mole per second, liter per mole per minute, liter per mole per hour respectively. Now here is the kinetics of the third order. A reaction is said to be third order if its rates depend upon the concentration of 3 or may not be the same. There are three types of the third order reaction with first reaction involving three different molecules of different reactants, that is A plus B plus C is equals to products. So the rate of the reaction is given by R is equals to K into concentration of A into B into concentration of C. Second reaction involving two different reactants means 2A plus B is equals to product. So R is equals to K into concentration of A square into B. Reaction involving three molecules of single reactant. So the rate of reaction is equals to K into A power 3. The constant K is called the rate constant for the third order reaction. Now we will calculate the formula for this rate. Now we will calculate the rate constant formula for the third order reaction. The formula for the rate constant of third order kinetics is equals to K is equals to 1 by 2T into x into 2A minus x divided by A square into A minus x whole square. If the initial concentration of A is equals to C naught at the time t is equals to 0, and at time t the concentration of A is equals to Ct, so we will get 2a minus x is equals to 2 of c naught minus bracket c naught minus ct is equals to c naught plus ct. So putting the values of a minus x, x and 2x in equation 4th, 5th and 7th into 3, we will get k is equals to 1 by 2t into 1 by c t ka square minus 1 by c naught ka square. Here are some important characteristics of these reactions are. So half-life period for third order reaction is inversely proportional to the square of the initial concentration of the reactant. So the half-life time period for this reaction is equals to Tf is equals to 1 by 2k into 3 of Ay square. Similarly, it can be shown that the time required for any fraction of the reaction to be completed is inversely proportional to the square of the initial concentration. Units of third order rate constants are liter square mole per mole square per second. If time is given in minutes or hours, k will have units liter square per mole square per minute or liter square per mole square per hour respectively. Some examples of third order reaction is third order reaction in gas phase. There are very few examples of third order reaction in the gas phase. The known reactions involve essentially two molecules of nitric oxide and one of the reactant, and the other reactants may be Cl2, Br2, O2, H2 or deuterium. The reactions are as follows. Third order reactions in solution. Third order reactions occurring in solutions are very rare. Some examples are reduction of ferric chloride by stannous chloride, reaction between benzoyl chloride and alcohol in ether. Reduction of FeCl3 by SnCl2 occur according to the following equation. 2 moles of FeCl3 plus SnCl2 give rise to 2 moles of FeCl2 plus SnCl4. The kinetics of the reaction was followed by mixing equivalent amounts of the reactant in the flask and drawing equal amounts of reaction mixture at regular intervals. These portions of reaction mixture are run into mercury chloride solution to remove or destroy excess of SnCl2. The resulting solution is titrated against standard potassium dichromate solution to find the amount of ferrous ions present. However, recent studies have shown that this reaction follows second order kinetics. Actually, very few reactions follow second order in the solution form also. Why reactions of higher order are high? It is observed that there are very few examples of third order reactions. Reactions of fourth and higher orders are very rare. This can be explained on the basis of collision theory. According to this theory, the chemical reaction occurs when the reacting molecules simultaneously colliding with each other with sufficient energy and proper orientation. The probability of simultaneous trimolecular collision is much less than bimolecular collisions. In other words, there are lesser chances of three molecules simultaneously colliding with each other as compared to two molecules in bimolecular collision. As a result, the reactions of third order are fewer than reactions of second order. Similarly, the probability of four or more number of molecules colliding simultaneously is very, very less. Hence, the reaction of fourth or higher order are very rare. Next is half-life period of a reaction. Half-life period of a reaction may be defined as the time during which the concentration of reactant is reduced to half of its original value. It may also be defined as the time required for the completion of half of the reaction. It is generally denoted by T half. The half-life period for reactions of zero order, first order, second order, and third order have been calculated during the earlier discussion. A brief comparison of all these is summarized as follows. For a zero order reaction, T half is directly proportional to A. It is obvious that for a zero order reaction, the half-life period is directly proportional to the initial concentration. For a first order reaction, it is clear from the relation that for a first order reaction, half-life time period is independent of the initial concentration of the reactant. For second order reactions, T half is inversely proportional to the initial concentration of the reactant. And for third order reaction, half-life period for a third order reaction is inversely proportional to the square of the initial concentration of the reactants. In general, for a reaction of nth order, the expression for half-life time is T half is inversely proportional to the initial concentration of inversely proportional to 1 by A into A ki power n minus 1. Molecularity of a reaction. According to collision theory, for chemical reaction to occur, the reacting molecules must collide with each other. The number of reacting species, molecules, atoms, or ions which collide simultaneously to bring about a chemical reaction is called the molecularity of the reaction. The molecularity of reactions can be 1, 2, or 3. In case of elementary reactions, the reaction which involves single step, a molecularity is simply the sum of the molecules of the reactant as in the balanced chemical equation. Following are some examples of molecularity of elementary reactions. Decomposition of hydrogen peroxide. Decomposition of hydrogen peroxide involves single species which form products. Hence, it is a unimolecular reaction and its molecularity is 1. The reactions of hydrogen iodide is a bimolecular reaction because two molecules collide to bring about the reaction. Hence, its molecularity is 2. In similar way, we can expect reactions which involve the collision of 4 or more molecules. However, it has been observed that reaction involving 3 or more molecules are uncommon. The reason of this is that the chances of simultaneous collision of 3 or more molecules are very small. In case of complex reaction, the balanced equation involves large number of reacting species is usually more than 3. In case of complex reaction, the balanced equation involves large number of reacting species, atoms, molecules or ions. But the chances of simultaneous collision of such large number of species is very rare. Such type of reaction takes place through 2 or more consecutive steps. In case of multiple step reaction, the slowest step is the rate determining step. The number of reacting species which occur in the slowest step or the rate determining step is called the molecularity of the complex reaction. It is clear from above discussion that the molecularity is always a whole number 1, 2, 3, etc. It cannot have fractional value, whereas the order of the reaction can have fractional values also. Mechanism and the rate law. We have learned that the complex reaction takes place through a sequence of 2 or more consecutive steps. Each step is an elementary step and involves the simultaneous collision of 3 or 2 species. The detailed description of various steps by which the reactants change into product is called the mechanism of the reaction. The steps which contribute to the overall reactions are called the elementary reactions. In case of multi-step reaction, each elementary step occurs at a different rate. Some steps are fast while others are slow. The step which occurs much more slowly than other steps is called the rate controlling or rate determining step in the proposed mechanism. The slowest step has occurred, the other steps will take place to form the products. Thus the slowest step determines the rate of the reactions. Here is a difference between molecularity and the order of the reaction. Now here are some methods for the determination of the order of the reaction. There are a number of methods for the determining rate law or order of reaction. The following methods are commonly used. First is use of integrated rate equation. In this method, the initial concentration of reactants and the concentration of one of its product is measured by a suitable method. Then any one of the following methods is used for the determination of order of the reaction. First is substitution method. In this method, the initial concentration A or C naught and the concentration of the reactant A minus X or Ct is noted at different intervals of time. These values are substituted in the integrated rate equation of 0, first, second and third order. The integrated rate equation which gives constant value of K decides the order of the reaction. Second is graphical method. This method is used when there is only one reactant. And this method appropriate function of concentration is plotted against a time. A straight line will be obtained only for the case in which appropriate integrated equation has been used. For a zero order reaction, K is equals to 1 by T of C naught minus Ct. Now we will plot Ct versus T gives a straight line with slope K and intercept C naught. For first order reaction, K is equals to 2.303 T by log C naught by Ct. Plot of Ct versus T gives a straight line which with the slope minus k divided by 2.303 and intercept log C naught. And similarly for the second and the third order we will calculate by this graphical method. Third is differential rate equation method, or we can also say want of differential method. We have discussed that in first order reaction the rate is proportional to the concentration term, and in second order reaction the rate depends on two concentration terms and so on. In general, the rate of nth order is proportional to the nth power of the concentration. So R is equals to K into C raised to the power n, where K is the rate constant and C is the concentration at any time t and n is the order of the reaction. For two different reactants, we can write R1 is equals to k into C1 raised to the power n, R2 is equals to k into C2 raised to the power n. Now taking logarithm on both sides, we will get log R1 is equals to log k plus n log C1. Similarly, log R2 is equals to log k plus n log C2. Subtracting equation 5 from 4, we will get log R1 minus log R2 is equals to n log C1 minus n log C2. Now the value of n is equals to log R1 minus log R2 divided by log C1 minus log C2. This order of reaction can be calculated by using these equations. The order of reaction n can be calculated if the values of rate R1 and R2 at two different concentration and C2 are known. This can be done by following methods. The small change in the concentration del C of the reactant is measured in small time interval delta t. The value of delta C by delta t is assumed to be constant in given time interval, and delta C delta t can be taken equal to dV by dt. Therefore, the values of R, that is dC1 divided by dt, that is R2, and dC2 divided by dt at two different concentrations C1 and C2 can be calculated. And hence there is a numerical which is based on the want of a differential rate equation method. Third factor is half-life period method. This method is also known as fractional change method. Half-life period of a reaction is the time during which the concentration of reactant is reduced to half of its initial value. We also know half-life period is directly proportional to initial concentration for zero order. Half-life period is independent of the initial concentration for the first order. Half-life is inversely proportional to the initial concentration for the second order reaction, and half-life period is inversely proportional to the square of the initial concentration for third order reaction. In general, for nth order, half-life T half is equals to T half is inversely proportional to 1 by A into n raised to power n minus 1. For two different methods, we will write this and we will get the formula for order of the reaction. N is equals to 1 plus log t half of 1 minus log t half of 2 divided by log A2 minus A1. Substituting the values of two initial concentration A1 and A2 and half-life periods from the experiments, the value of n can be calculated. Next is Ostwald isolation method. This method is employed in determining the order of reaction which involves two or more reactants. This method is based on the principle that the contribution of the reactants taken in excess to the order of reactions can be neglected. In this method, the concentration of all but one reactant are taken in excess. Thus, the concentration of those reactants taken in excess will remain almost constant, and the concentration of reactant present in small concentration is varied. The rate of reaction will vary with the concentration of the isolated reactant. This helps to predict the order of reaction with respect to one reactant. In this way, one reactant is isolated from others and observed. This process is repeated with other reactants one by one, and order with respect to each reactant is determined. Thus, overall order is the sum of these orders. For example, AA plus BB plus CC is equals to product. Suppose we isolate A by taking B and C in large excess and get order of reaction with respect to ACX. So overall order of the reaction N is equals to X plus Y plus Z. So here alternative method is also. In this method, the initial concentration of any one of the reactant is changed and the rate is determined. From this, the order with respect of that is calculated. For example, A plus B is converted into products. The concentration of A is doubled, tripled, etc. And the effect on the reaction is observed. The order with respect to the reactant A can be found. The same procedure is followed for the reactant B while keeping the concentration of A is constant. The variation of rate with respect to reactant B observed and the order of reaction with respect to B is calculated. The overall order is the sum of the individual orders. Now here are the examples on Ostwald isolation methods. Now next and last topic of this chapter is effect of temperature on the rate of reaction, that is Arrhenius equation. In adenine, Arrhenius give the quantitative relationship between temperature and the rate constant and hence the rate of the reaction. This expression is called Arrhenius equation and it is written as K is equals to A e raised to the power minus E divided by RT, where A is constant called frequency factor, EA is the energy of activation, and R is the gas constant, and T is the absolute temperature. The factor E raised to the power minus EA divided by RT gives the fraction of molecules having energy equal to or greater than activation energy EA. The activation energy EA represents the minimum energy that the reacting molecules must possess before undergoing a reaction. Activation energy cannot be measured directly, but it can be calculated using Arrhenius equation taking as follows. Now we will do take it logarithm on the both sides of equation 1. So we will get ln k is equals to ln A minus EA divided by RT. If K1 and K2 are the rate constant for the two reactions at different temperature T1 and T2, then ln K1 is equals to ln A minus EA divided by RT1, and ln K2 is equals to ln A minus EA divided by RT2. Subtracting equation third and from, we will get ln K2 by K2 by K1 is equals to EA by R into 1 by T minus 1 by T2. So we will get log K2 by K2 is equals to EA 2.303 R T2 minus T1 divided by T1 into T. Thus, knowing the values of rate constant K1 and K2 at different temperatures T1 and T2, the values of activation energy can be calculated. Equation fifth can also be used to calculate the rate constant at any temperature. If the rate constant at another temperature and the value of activation is known for particular reaction. Alternatively, the energy of activation EA can be calculated by writing the Arrhenius equation in the form of equation of a straight line. So equation 1 may be written as ln is equals to minus EA divided by RT plus ln A. 2.303 log K is equals to minus EA divided by RT plus 2.303 log A. Log K is equals to minus EA divided by 2.303 RT plus log A. The equation is the form of y is equals to mx plus c. When log K is plotted against 1 by t, we get a straight line. The intercept of this line is equals to log A, and the slope of this line is equals to minus EA divided by 2.303 R. Knowing the values of slope and gas constant R, activation energy can be calculated as activation energy is equals to minus 2.303 into R into the slope. So that's all for the this chapter. Thank you and have a cheerful day.